So the next we have panel discussions. It will be moderated by Professor Sarit Kumar Das, and we request senior members present here, Professor David Weiss, Professor Thomas Laurel, Professor Dimos Polikakis, Professor David Kare, and Professor V. Kumaran to be on the dais. Welcome back. This is the last session for today before we head towards the Westin for the gala dinner, cultural plus gala dinner. So this is going to be the panel discussion session, where the idea is that we look at how the field of micro nanofluidics evolved and look at some of the current challenges and how it's going to be in the coming years. So for that, I request Professor Sarit Kumar Das to moderate this session.
Thank you, Professor Sen. You know, Professor Sen has made this conference perfect. So everything is very structured and naturally very disciplined. And I am a quite indisciplined person. I still remember one small story, anecdote. When I was in Germany as postdoctoral student, one of the students of my mentor, Professor Roetzel, asked him for a recommendation, a letter. Professor was not happy with him, with his work, and he said, "Don't take it from me." He said, no, I need a job, so I need you are my doctor father. In Germany, it's called doctor father. So, he said, okay, come after 2 days, I will give you recommendation. And he wrote the recommendation and said, Professor Das, look whether the English is all right. So I looked at it, I said, you have given good recommendation, you could have given 2 days back. He said, no, I have written there. You read it, what I meant, I read it. So I said, what? I said, there was a line, he is very punctual, he comes in time and goes in time. So the thing is, he said that the person, researcher, comes in time is fine, but if he's going in time every day, then he's not a good researcher. So this is what I feel, that it is so structured that Professor Sen's students have even given me about 100 questions. So I will go probably a little bit unstructured. And I propose that let's do it this way. Everybody makes an opening comment in the panel. And then we go to you. And we take your questions. And the opening comments can be small. I mean, something like 2-3 minutes or 3-4 minutes. And then we go back to the audience, take questions. And then at the end, everybody makes a concluding comment, maybe of 2 minutes. This is what I propose. And to start, what people should talk about, we are talking about the past, present, and future of microfluidics. Now, I think all of us have read that paper by George Whiteside, which says the origin and the future of microfluidics. But that was written in 2006 in Nature. And from then, lots of water has gone through Ganges and Rhine and everywhere, Mississippi. So I think the scenario, we would like to know from you whether that has changed. What was said to be the domain, aim, direction of microfluidics, has it changed in the past? Does it face any formidable challenge today? And are we able to see the future? If we are able to see at least for the next 3, 4, 5 years, that will also be a good experience for others. So I would say past, present, future of whichever aspect the famous people around me, they are willing to share with us, I would leave it on them. So with this, I start the opening comments. I will say Professor David Weiss can do the first one.
Okay, so we're supposed to keep it short. I'm going to keep it very, very short because I think you guys should say things more than me. If I knew what the future was, I'd be doing it. So I have no idea what the future is. I really don't. George is one of my real scientific heroes. I shared a student with him, just one of my last students, to understand what he did, whether I could learn something about what to do. And I realized that what he does and what I do are very different. So he writes these review papers. I don't. So I think with that, I'll just leave it and let other people make much longer introductions. And let you guys ask questions during my time.
Okay. I think we will go to now Professor Thomas Laurel.
Yeah, so I need to go back to George's paper in order to answer your question, and since I don't quite remember that, all that's in there, but and if I knew the future, I wouldn't be here, for sure. I would be doing something else, so that's the billion-dollar question, I mean, predicting the future, but what I see is, though, that I mean, I've been in the microfluidics game for quite some time, and there has been a shift from very fundamental engineering in terms of material technology, how you build devices, also understanding fluid behavior as you scale down and come down to even nanoscale now. Understanding is much better today. So many of the building blocks are there, and we see things that not only doing unit operations, but we are seeing systems being built, and now not only systems and analytics, but we see a lot of biology. You see the whole field of biology and medicine is moving into this field, making more and more intricate systems to try to understand what is really going on and decipher in biology. And my future is more, sometimes I say to my students, we are in the biology and medical field, thanks to technology, where electronics was somewhere in the early 60s. So we're going to see tremendous development coming up now. We already have seen that, and we tend to forget it, though, that the ability of sequence genomes over the past 20 years has evolved tremendously. I mean, the orders of magnitude in saving money and speed of doing that, I mean, we just take it for granted. And this is just the beginning. So I think there's a bright future. You guys are going to have to take it to that tremendous success that's ahead of us. So I don't know, I'm just giving you an enthusiasm and future belief that this is a good field to be in.
Thank you. So the next I would go to Professor Kumaran. Maybe one this side, one this side.
Yes, thank you, Professor Das. I work in the rather unglamorous area of fluid flows and all of this stuff. And what I would say is that, of course, you can do all of these, the developments in materials and reagents and reactions and so on. But at the end of the day, to make it actually useful for people, what you need to do is what you would unglamorously call plumbing. And that is a critical component for which we do not have the kinds of rules that we have for electronic devices, for example. Fluids flow very differently from electrons, and as yet there is no coalescence right now on how we are going to do the plumbing to achieve all of these multiplex reactions and so on in low resource environments at cheap cost and low power. And so I don't think there is right now a consensus on this. And that provides a tremendous opportunity for all of you to work in this area. At some point, maybe there have been promises. I discussed one spectacular failure in one of in my talk here. There have been promises, there have been failures, but we need to do the hardcore engineering required to make it useful for people on a large scale, especially because commercially you're competing with laboratories which do these same things very cheaply in India. I mean, I know there's a big difference between costs between here and the Western world, but here things are done very cheaply by innovations at the local level, and one has to compete with that. And so if you can make a difference here, I think it'll make a difference everywhere.
Okay, so the other aspect, which is very practical, very important, as he said, plumbing in a very quoted way, but I think it's very important. The laws of how to make a circuit and how to make understand the fluid flow at that level with all the complexities. What he has also said during his presentation, this flexible boundaries and so on. So the next I would invite David Correa.
Well, I don't know why I'm here. I'm not working in microfluidics. I'm working in something which is called soft matter, which used to be called complex fluids. So the only thing that I can say is that complex fluids can be a simple liquid in a complex situation. Even just a drop is something which becomes complex because of its surface, or it can be a complex fluid per se. So mayonnaise or ketchup is a complex fluid. And the temptation today, where we had many progresses in both directions, would be to mix them. And so here, it's sometimes something called in painting manierism, where you go to Byzantine things. And so it would be more an advice, because it's a temptation that we all have to mix two things which are complex. And so my advice would be the following. You can do that. There is some probability that you find something interesting, but only go there if you extract simplicity, if what you do is not complexity to the square, in which case it will be very, very useless. So we can follow this temptation, I think, but we must be very wise when we do that. And I think it's a way soft matter is going today very often.
Thank you. I will go back now to Professor Tropia. Probably he can also take the same plea that I'm not a microfluidics man, but but he of course does with fluids at a micro scale. There's no doubt about that.
So if David doesn't know why he's here, then I don't know at all why I'm here. But but I'm going to also take the word up about temptation and advice. But I'm going to do it in a different way, because as you know, I'm editor-in-chief of Experiments in Fluids, and every morning I have 4 or 5 manuscripts on my computer and have to decide desk rejection or not. And my advice comes from that experience, and it applies to microfluidics. And there's 2 things that I wanted to say. Number one is, I think if we look back to 2006 and now, one thing has definitely changed, and that is that we have technologically these fast cameras. I don't think I saw any presentation that didn't use a high-speed camera. And the temptation is to something that I call observational science, which is actually, that's ironic because it's not science. And that brings me to so that's a temptation. You make fabulous pictures and movies and you think that's science. And that brings me to the temptation part of what I wanted to say. And that is that the fast movie is not enough. You have to understand the physics. And when I see presentations where things are not in dimensionless form, then it's a little bit exaggerated, then I immediately register that person has not understood the physics. And so that's my advice, is if you can't put your results into dimensionless form, you're not finished yet, and you shouldn't yet be presenting. A little bit exaggerated, I realize, but in the long run, you have to do it that way. Otherwise, you get the desk rejection.
Yeah, I will come to the last one, which is, that's why I kept Dimas at the end, because he is surely a microfluidics person, and he has done observation at the purest and highest level, followed by or assisted by equal exploration of physics and the mathematics and whatever you may say, even simulating a very complex situation. Everything Dimas has done. So I think you should conclude the opening session well.
Well, thank you for this opening remark, but it takes away my opening line, which was, I also don't know why I'm here. So, so anyways, I have a statement on this, and I had the chance to think a little bit as the other people were presenting their statements. And mine goes like this. It's kind of generic, all right? So there is, in research, you have a phenomenon you want to explain, let's call this physics, all right? And then there is utility, all right? And you've seen in this conference both, all right? So you have seen some works that the excitement comes from the explanation of the phenomenon. Either it's a new phenomenon, new to you, or whatever. And then the utility of this, although sometimes you're forced to say, oh, this is going to be used for cars and airplanes and so on and so forth, really is not there. And on the other hand, you have something that the physics is done very fast, but then it has tremendous utility, all right? So, and then there is, of course, some complexity sometimes that comes with that. And so this is sort of the spectrum of where you have to decide what you're going to be doing. So there is a tremendous merit, I think, of both sides. If you can mix them, then, of course, you're in a very good position. But what I've tried to do is do what I love to do. All right, so I think that's my advice to you. You have a spectrum, and then try to see what matches because you only live once, and life moves in one direction. So choose carefully what you do, and make sure that it gives you satisfaction in what you're doing.
So with the opening remarks, one thing is very obvious that there is a progress. Otherwise, we would not have been here. I mean, if I talk 2006, etc., I mean, beginning of this millennium as some kind of a beginning period, today in almost a quarter of the century, we have definitely made progresses. And progresses are, on one hand, in measurements. It's not just the photography, but the micro measurements of everything, pressure or stresses or whatever it is. This is on one side in the measurement, but on the other side also the fluid flow in microchannels and gas flow, liquid flow, phase change, particles in we have seen just now presentations on how which may not be in microchannels but may also be in microchannel where fluid evaporates, fluid condenses with particles, without particles, and so on. The other thing is, of course, even applications are very important, and one of the major applications which is coming, everybody has said about that, is biology. But even apart from biology, there are other applications, a number of applications, which we can talk about here. So with these opening remarks, we would go to the audience for some questions.
Yeah, I would like to pick up that point, applications versus fundamentals. So, I mean, my question would be, do you agree with me or not? And I mean, now I'm going to outline the point that, I'm curious about. So this is, I have been in that area, microfluidics, also for a while, but I'm doing fundamentals. And I think this conference is in a way unique because it brings together people that work on fundamentals with people who do, let's say, applications mostly. But if you look at research funding, I observe a certain trend that's I think a worldwide trend, and that's not only in microfluidics, that's in different areas, that in the past couple of years, there's an increasing trend towards you need to justify your research because you need to save the world, right? You need to, let's say, sketch a scenario that you can save the world, and because you solve a problem of whatever, CO2 emissions or something like that, and then that would be what I would call top-down research. Then you basically define work packages, how you can save the world. But this is not the only thing. Curiosity-driven research, insight-driven research is really important. And my perception is that this isn't valued as much as it was valued 20 years ago, 30 years ago. And I think that's a dangerous trend, and I think we should counter that trend. And my question would be, do you agree or not?
Who is to take? Yeah, sure.
I was not planning to speak a lot, but suddenly I like very much the question. So the remark is very, very simple, in my opinion. My remark is very simple. Your question is, of course, difficult. Maybe I could take as an example, instead of something long and theoretical, something that Dave White might know very well, much better than I do, which is the Exxon thing in Annandale, which was this dream team of a very young physicist, which was built for, in principle, practical applications. So this is a research which was driven by applications. And what is interesting is that I think that most of the things they found, at least to the best of my knowledge, are things which could be related to what is soapy water, for instance, and discovery of onion phases, which have nothing to do, I think, with oil recovery. And so for me, this is exactly the question Stefan asked. What is research? Is something where you give answers to a question which was planned to have a completely different kind of answer. So you discover something which was not planned, and applied research, unfortunately, is planned. And so this is something we must always have in mind, because if we do something where the only goal is to ameliorate what is already there, which is applied research generally, there is no discovery. So we can follow the path of applied research, but we must be extremely free of what we are doing, because the plan is not to say that in one sentence. If you are asked to get a better light, you do not discover the laser.
So you're right, David. I did spend some time at Exxon, which is a fabulous place. And I learned that there's no such thing as basic research and applied research. There's only good research and bad research. And I think you make a real mistake if you say you want to do curiosity-driven research. And I tell my students the same thing. You can be curious about anything. There's lots of things to be curious about. And there's nothing to say that if you have something that may have an application, you can't do really first-rate science about that. So me, I'd rather do something that's absolutely first-rate science that changes the way scientists think about things, but still has some use, some application, that also changes the world, that makes the world better. I don't see why I can't do both, and that's what I try to do. So I don't worry about this sort of blah blah. We have to do curiosity-driven research. Of course we have to do curiosity-driven research, but you can be curious about a lot of things. Why not be curious about something that's really also really important? That's just my perspective.
Can I briefly reply to that? Yeah. So, but I think this may maybe the way how some people are thinking, but there are nerds. There are nerds who are just curious about things, and these nerds are not thinking like that. And sometimes
I'm a nerd too. No, I'm sorry. I disagree with you. I really disagree with you.
I'm a nerd as well, and
yeah,
I also disagree with you.
You can be a nerd about a lot of things. What makes you curious? Anything can make you curious.
Yeah, but it's not always application.
No, but,
I mean, there can be a physical phenomenon.
Let me tell you one thing, of course. One part of your other is, of course, debatable. But one part I do agree, which is true everywhere, including India. It's much tougher to get, funding for a fundamental work. So it's this is becoming, whenever, and what happens, it's like...
Could I take that up?
Yeah, I will.
Yeah.
I will
this is exactly the point I have to take.
See, the thing is, it's like, somebody was saying that film censoring, there is a censor board in India, so they censor, and somebody said, you see, once they censor very badly few films, then all other films get self-censored. Because the film director understands what will go through and what won't go through, and he will not intentionally short those shots which will not go through. So it becomes So our projects that we write, I mean, how many people in last couple of months in India, I'm talking about, has written a project on very fundamental aspects of understanding.
So this is
self-centered because I know it won't be funded. So why waste my time?
Okay. Why are we here? So I also felt that you've misinterpreted Stefan's question. So it's not about what we think and what we feel, and we all have our personal, desires and wishes and passionate things. But I think what he's talking about is something fundamentally different, and that is the funding and the possibility of funding. And this is not what you talked about. And when I look, and I think he's got a good point, because we have that in our hands also. So I'm sitting on the ERC boards and things like that. And of course, and I'm sitting now on the Cluster of Excellence in Germany, and you get these funding criteria. So evaluation criteria is what we're talking about. And the evaluation criteria is a list of things that you're looking for when you decide, should it be funded or should it not? And those things read something like, is it groundbreaking? Is it high risk, high gain? I mean, these are things that you probably never think about when you decide, what am I going to do?
Kidding me? I think about it all the time.
Yeah,
are you kidding?
Yeah, and
you have no idea what good research is. You don't even know numbers.
That's exactly the reaction I wanted, because he knows what the evaluation criteria for an NSF is. And so I think what we have to be talking about is, are that the evaluation criteria that we want? And have we got the possibility of changing that or modifying this evaluation criteria? That's really the problem that we're talking about.
Okay, now I would, the discussion is going towards very sensitive, topic of funding and all that. Shall we come back to microfluidics? That's my job.
The chairman has the mic, so.
No, but
I have to say something.
Yeah, make it.
Because right now I'm a member of the Presidium of the Swiss National Science Foundation.
Yeah.
And we are actually funding people, right? So, and we're funding people from social sciences all the way to the sort of, let's say, engineering sciences. So, and I'm kind of all over the place on this. So I feel you, and I agree with David too. So personally, some of my most important fundamental work came out of industrial collaborations. So so therefore, I would worry less about sort of labeling things, and I'm with you on that side. At the same time, it's true what you say. You sort of have to fake an application in applications of the National Science Foundation to fake some relevance and so on and so forth, because the system is set up that way. So, and that's what it is. And it is more if you're, a physicist, an engineer is sort of supposed to be like a physicist with a purpose, So engineers are more used to, connect to applications than physicists. And physicists were allowed to be sort of more, let's call it between quotation marks, creative and so on and so forth. And the two are converging now somehow. And that makes, of course, some people uncomfortable. But what you say is certainly is true as far as the research for the funding environment.
Yeah, so I agree with you that funding is an issue, and it's driven very much by politics. But at the same time, we've all worked our way through the system in terms of getting funded, and once you're there, I think we're all clever enough to do that curiosity-driven, not fully justified research where you really want to do something totally crazy, but you want to investigate that anyway. And you do that sort of under the radar until you have found that spot of hot science that Dave is sort of indicating here. So I think we just have to live with the system. We cannot change that upper level of decisions, but we just have to work our way through it. And I think we all do it. We all sort of moonlight our secret studies until we have something good to come up with, and it's just the way it is.
So when it comes to microfluidics, I think we are in between the two extremes. One extreme is Alva Edison, who said, nothing useful is, if it is not useful, it's not interesting to me. That's one end. And the other end is a scientist, a mathematician from this land, Srinivas Ramanujam, the great mathematicians who knew the infinity, as that film came up. And he said about that so-called the Ramanujam number, somebody asked him, what is the use of this number? And he said, I pray to God that it never comes to any use. Just let it remain for its beauty. So there are two ends of the spectrum. Microfluidics is somewhere in the middle. So some more questions we will look for.
Hello, my name is Sasidhar. So one of the problems with microfluidics becoming applicable is that actuation processes, which are probably bulky, so they cannot really go into a medical field directly. Like a doctor, if he wants to diagnose, he has to use syringe pumps, he has to use external fields. So these are the things which are probably making it difficult to become applicable, right? So how long would it take, or is there a chance that in next decade that it can become more portable and more applicable?
Okay, so before I go to anyone, I have some answers. Is this, that when these kinds of research started, probably we used very sophisticated things, but slowly people have realized that there are even much simpler ways to do it. For example, today there is one field called paper microfluidics. Okay, very simple. You can have designs in papers and take analytes, and you can do analysis. Again, if you are saying syringe pump, etc., well, today it may be very sophisticated, but if we start using it in millions, naturally the technology will improve, it will come down. And so I think there is progress to make it, particularly in diagnostic, it has made good progress. Therapeutics, well, it's still a long way to go. And understanding, I think it can do a lot. That's as far as bio is concerned. The others I would ask.
Before someone answers, just to complete my question, probably I did not clearly state it. So I don't see anyone has presented on actuation techniques in microfluidics. So if that changes, if it becomes much simpler, I think it becomes a lot more applicable in future.
Probably.
So the possibilities.
Anyone wants to take?
Yeah, okay, so I can say a few things. If you're talking about actually translating it into applications, somebody has to fund it. And that funding usually these days comes in what is called venture capital funding. And for that it is essential that those who run venture capital funding have a good idea of technology, which by and large currently they don't. And so usually they put money after somebody else has put money, after somebody famous has put money. So that is one roadblock. The second one is that very often governments try to fund these things, at least at the initial stage. The problem there is that the timescales for government funding are much longer than the timescales for these kinds of funding. So a 2-month delay will result in the company going bankrupt, for example, whereas 2 months is a very short period for government funding to be. So from the commercial point of view, those are the primary roadblocks. There's also a sociological issue. That is that doctors, if you're talking about doctors, they're used to doing things a certain way. For example, they write their prescriptions a certain way, they look at certain measures, and so now you have to make your device actually produce those measures. You cannot expect the doctors to change what they are looking at, right? So they have certain gold standards, and you have to make a device that actually produces that, even though that may not be the easiest one to get. Okay, so that is the other sociological issue. And as I said, scientifically plumbing is still an issue. Okay, we don't have good, for refineries and so on, there are standard ways in which you can design pipes. Here it is not, and that's for various reasons. You typically have charged fluids with microscopic entities in them. And so very often the motion is coupled with electric fields, surfaces, surface charges. They're usually at scales where you cannot use a continuum approximation. And all of those complications are there. And so any design toolbox that we make has to have a much larger number of layers than what is there for macroscopic applications.
Okay, before we go to the next question, Can I throw up one question which may be applicable to everyone here? That's the manufacturing, of the microfluidic devices. There is one possibility today, probably, with the 3D printing, whether and how it can replace some of the, standard techniques like photolithography, etching, making channels, etc., etc. Because my personal experience is it can reduce cost and time, both of them. And of course, you can go for more complicated designs if you are having these. And even the other thing that you can control, which is very difficult to control in photolithography, is surface conditions, surface roughness and all that. So anybody on that?
Now, first, I would like to just link back to your question about actuation. I think we had a couple of talks talking about actuation. I spoke myself about how you're moving particles or cells with micro devices, easily portable. We heard about magnetics today, how you move particles around again. I think you're thinking very much about fluid propagation, how you move fluids.
Yes.
We heard a lot about capillary forces, and that's one way that we have seen a lot come along. And generally, I think that it has not been the main focus in the field of microfluidics necessarily how to drive the fluids, but rather what you can do when you drive the fluids and all the other mechanism and problems that you're facing. So there's been a lot of focus on, as I mentioned, doing all the other unit operations that you need to build a system. And now as we are at the stage where we can build systems, the engineering is there, the manufacturing is there, we can start to think about what you're talking about, how we drive the fluids and in a more simple and portable way. So I think it's going to come. It's there, and it's for you to do it.
Anyone else about manufacturing, fabricating the...
It depends. I can maybe make a small comment. You mentioned 3D printing. The resolution is not there nowadays. If the resolution reaches that of lithography, going down to E-beam lithography and so on and so forth, which is not going to happen anytime soon, then I see them as competitive. But right now, the domains of their application are not overlapping. So, yeah. So therefore, I think I would let, yeah.
At least for biology, where we need more like hundreds of microns, I think 3D printing can work.
I think David can. Yeah.
I think the reason it's not there is actually a very simple physics reason. If you'll apologize for thinking about something fundamental, even though it's applied, but it's basically because it's an additive form of manufacturing.
Right.
And if you want to have high resolution, you have to add very, very small things.
Right.
And if you add very small things, you can't make larger scales. And that's where the limitation is. And so I also have the experience that we never use 3D printing for our microfluidics.
Right. Unless that barrier somehow, some idea of his kind that we didn't fund is overcome, so.
Yeah, if I could just
Yeah.
I mean, I think if there is a compelling commercial reason for manufacturing processes to be created, they will be created. So if you take the classical example of silicon, the chips that we use every day, they are extremely high purity. I don't know if anybody knows, but silicon has to be purified to 99.79% before it can be used for chip manufacturing. And that is done by a series of very energy-intensive steps. But we always get the 99.79s. Okay, so it's a part per billion, this thing. And the reason it is routinely done is because there's a small commercial, there's a big commercial advantage to being able to manufacture chips that way. And I think if we get to that scale, then these manufacturing processes will evolve. We are not there yet because we don't have standardized ways of converting a circuit onto a chip. Okay, the way that a circuit is designed and then just fabricated onto a chip, those kinds of ways are not at present available for microfluidics, and that's the reason. If and when that is done, then automatically we will be manufacturing processes will evolve if there's sufficient value in it.
Okay, one more question we'll take. Yeah.
let's go not to 2006, but to 2046. Here in one room we have laboratories with very different level. Somebody has overcome the problems already 10 years ago, the same problems that people face now. And I wonder your opinion about we are used to cloud computing and all computers are the same. We don't care that somebody has another architecture than another people. I wonder about cloud chemistry laboratories and microfluidic cloud laboratories, so that you just send your task, it's all standardized, and you check your chemistry or biological experiments somewhere in a big remote laboratory. And it seems like microfluidics offers such possibilities of creating such big national centers. So what do you think about this?
Yeah, please. What a boring existence. I'm glad I'll be dead by then. I wouldn't want to do that. Sorry, I'm old-fashioned. I like to do experiments myself.
That's a fairly interesting comment, actually, and probably one that not many of us have thought about before. But I'd like to draw an analogy. I mean, the fact that you have central and, let's say, flexible and large facilities. Now, I'm going to leave microfluidics and go to wind tunnels. And, you know, there's 3 or 4 excellent cryogenic wind tunnels in the world where Mach number and Reynolds number can be matched for, you know, for normal flight passenger aircraft. And these things are booked out. I mean, you just don't get, and they cost, I don't know, 20,000 euros an hour or something. And that's an example of where not everybody has their own cryogenic wind tunnel, maybe every continent, but not everybody. And that, you know, you send your experiment there, and actually you don't have much to do with it when it's running. I mean, they do it. And that's a little bit of an analogy, and I think, obviously at a completely different scale, also maybe in terms of money. But let's think about that. I mean, what are they actually doing then in those type of facilities? They're not really doing, I'll not say curiosity-driven, but exploratory research they're not really doing. They're doing sort of engineering type of research. You know, okay, can we make the flap better, or can we test this CFD program, the results of the CFD? So I think if I had to answer the question now, I would probably say that's not in the future for the things we want to do. Maybe there are certain, you know, if you have to test 100,000 different you know, recipes for some drug, maybe you could do that centrally and but not the kind of thing we're doing.
Yeah, so I took a different sort of take on the question here, that basically what you can do today is if you have a request on a certain performance of a microfluidic solution, you don't know how to do it, but you can rather quickly go out there in the cloud, download the papers you need to actually do all of this, and it's out there, it's in the cloud. If you go back 35 years, it would have taken you several years to actually get access to those papers, and you wouldn't really have that information yet. But today, you have a tremendous amount of information out there, so it's in the cloud, allows you to actually gain that information and knowledge in a very, very short period of time. You will not be able to do the experiments in the cloud. You will have to do them in Dave's lab, and he will do I mean, he doesn't necessarily spend all the time doing the fabrication, but he wants to do the physics and the fluids manipulations in those systems.
Don't you just ask ChatGPT? No, but anybody else? Yeah.
Okay, you're looking at me every time. I don't know what, so I have to come up with an answer right now. So, I mean, I think, I don't know how you asked this question. To a certain extent, centers like that exist in terms of, you know, but the reasons financial, you know, shared facilities, I call them, all right? But those are not really research. You know, don't do research, because part of the research is, if you want a device, the device is part of the research. You cannot, by the time you're done with your device, you're almost there, all right? Because, you know, you use a lot of physics we saw examples of that, to design your device, and, you know, if you need some measurement or some surface topography from some expensive equipment, there is these facilities of shared facilities where you can do that. So I cannot think, not only because it's boring, but it wouldn't be research of any cloud for chemistry that does your research. it would be done some measurements, but that's how I see it. Yeah.
I'm going to bounce on Dimos and others. Cannot be research because it's, as Cam said, it's limited in time. Okay, so you buy a slot. Okay, and so when you do that, it can just be what you expect to be, something like that. Research is a way, is something which is you cannot, of course, anticipate the time, and you know that you need it, and so there is no. So it can be analysis, it can be anything like that, but not research. There is a very beautiful quote by a French painter who was very famous. He died last year, very old, and he said something which is very general for all of us, I think. He said, "What I am doing teaches what I am looking for." So it's exactly research. So it's because you do something that you realize what you are looking for. And so this is, of course, completely different from applied research, and it's also completely different from a place where you would go for one day, for instance, where you know in advance what you are going to do.
Well, it's because this panel is heavily loaded against the young man. So there has to be some devil's advocate, and let me play it. Let me play the devil's advocate. Well, it's known very much that the person who said that personal computer going to every person in a household is an absolute improbable proposition, and this was told by the president of IBM, the top man in computer world, and we know what has happened. So I am not, if we are saying that we are outsourcing research, no, that's not. But there are many things which can be done centrally. For example, even fabrication. Will there not be standardization of fabrication? There may be. There may be, standardization, not one, but 20 techniques, and I say I want this technique and I want this kind of a surface finish with this kind of channel, and it's done centrally. Why not? Why it cannot happen? And the things which we think are very unique to me will become something of a very, very common thing. So because he said, I'm not talking of 2006, 2046. Well, even 36 we don't know, 46 is far away. So I am not completely, I don't see, because I see, the thing, the way wind tunnel has gone, computer science has not gone that way. So every domain has got its, that's why we are here. So the microfluidics is not fluidics. It goes a different way. And that way, maybe making channels and then making connections, plumbing, that can be standard. Why not? And imaging, measurement, that can be also standard. So why not when everything cannot be standard. The research, its basics cannot be standard. But there are many things which can be standard, and if not like cloud computing, but large conglomerates doing, don't we see today a work done by authors from Europe, North America, Australia, and Southeast Asia, authors from every place? We do see. So why not? Was it thought about 50 years back? Never. So why not? So future we don't know, and microfluidics may be an area in which we can see such kind of collaborations. Let's leave it to future. None of us know. Nobody has seen tomorrow. So shall we close the questions, or do we have? Okay, one more here. Okay, these two we will allow.
Yeah. Thank you, panel, for allowing me this opportunity. So I have more. So this conference is also related to soft matter. This conference is also related to soft matter, as in the title itself. And I work particularly on the numerical side, so I'll be asking a question regarding that. So recently, I'm not sure if you are familiar, if the audience is familiar with active Brownian particle model, but recently a lot of papers have been coming up where they have shown that this model, which had been used since roughly 25 years, is not that good after all. Other models are showing much better promising results to to explain the phenomenon that occurs in natural and artificial microsignals. So that brings me to a more like a broad question as to, are there any sort of models or any assumptions that we might have taken or people might have taken in the initial days of research just because they showed some initially promising results, but as we are probing further, we are finding out that they may not be that correct. So is there a requirement to go back and visit the priorly defined models and the assumptions that have been taken over the years in research?
Okay. I would say, are you talking of revisiting the assumptions or the basic methods that we have taken? In fact, if you look at, there are many completely new kinds of techniques which have come already. Lattice-Boltzmann, for example, is one technique. Molecular dynamics is another technique. In turbulence, you have got other techniques. Apart from modeling, DNS is another one with the increase of computing power. So there have been effort to develop newer techniques all the time. You mean to say some of the assumptions we revisit? Yes. For example, the greatest example is, particularly in the domain of microfluidics, people challenge this concept of sleep. There are people, one was Professor Howard Brenner in MIT, and there was Professor Durst in Erlangen. So they came up with the Navier-Stokes equation with self-diffusion term. And they said, the sleep is a nonsense thing. Maxwellian sleep doesn't exist. You have, even in microchannel, there is no sleep. You solve Navier-Stokes equation with the additional self-diffusion term, you will get the same result. Yes, even the assumptions have been revisited. So that is there and that will always be there. We have to go after them, whether it is in technique or in the basic fluid mechanics itself. It's always challenged.
Yeah, we are talking about like mass production of the devices. But once if it is mass produced, how are we going to take care of the environmental impact these devices will create?
Yeah, I think very important.
Yeah, so yes. That has to be built in at the fabrication stage itself, the life cycle management.
Yes. So is it established already?
I don't know if it's established here, but certainly in many places it is established. That forms an essential part of the curricula in many places. Okay, that is, when you fabricate something, you have to know what's going to happen at the end of the life cycle, and the manufacturer has to have some way of taking it back and doing something else with it. So that kind of thing is there. It's a much bigger problem even in our normal consumer goods. Right now, we don't have ways in which those can be taken back. Fortunately, we have unfortunately, we have in this country, we have a large range of wealth and incomes, and so you can always find someone who will get value out of things that most people will not value. And so we are right now fortunate in that respect, but when and if the average economic conditions improve, that's going to be a problem for us as well.
So I'd like to maybe add a couple of words. So when I moved to Switzerland from the United States, it's almost 30 years ago, the president, I talked to the vice president of research there, and he told me, we have these priorities and so on and so forth. And then there's this thing called that our president likes, and we let him have it because he likes it very much. It's called sustainability. Right? So it's his thing, we don't bother him. So that's what shows you, it shows you what the thinking was 30 years ago. That's not a very long time ago, right? And nowadays, of course, the concept of sustainability is everywhere. In the Swiss National Science Foundation, it's almost like a blanket sort of criterion for everything we fund, to be in alignment with this sustainable 16 or 17, I don't want to make a mistake, sustainable goals. So you talked about basic research. Now sustainability is a criterion that you have pretty much fulfilled. And of course, there's this branch of sustainable manufacturing, all right? So this is part of this whole thing. And right now, of course, in the industry, many of them are taken into account into the fabrication of many products from the beginning to the end of the life cycle. So it is really going that way, and I think,
Here it's called end-of-life engineering.
Right. So effectively, it's nowadays and in the future, I expect it to be more and more of a criterion for development of products.
Yeah, so I think it's a very important question you're raising, and as you said, the awareness is there on a very broad level, and the blanket that we need to think of that all the time. And I think that the European Union is pushing a lot on that specifically, and in my own field, piezoelectric elements, just a few years from now, we cannot have lead in those. That means that we need to do a total shift in the way we do things. And it's already on its way now. There are coming up now piezo ceramics that don't contain lead anymore, and then will fulfill the criteria. So I think these sort of directives also help and push, enforce new developments, and also fundamental science in terms of doing that, because we just take things for granted that we have certain devices or certain technologies, and we don't even bother thinking of doing it different. But as soon as there is a pressure to do it, we solve it. I mean, we could solve the vaccine over 12 months, basically, when we really needed it. We could do it, and before that, it took many, many years. So as long as you push the right buttons, I think the scientists will actually be there to do it.
One thing I must tell you, the newer technologies, for example, the nanotechnology, which we started thinking for last, maybe 25, 30 years, even forget about the sustainability, that is environment. Even what's the effect on human being? How much has been studied? Sometimes I feel very guilty that my students have handled nanopowders. I really don't know what happened, whether it had gone to their system, affected them or not. It's something like, when Madame Curie did radium experiment, they did it in open tubes and, poured it, and because they were not curious about the biological effect. They were only looking at physics of it. And all of them died. The whole family, excepting the, father, Pierre Curie, he died of course, accident. But all others died of cancer, including Joliot. So we don't know, really. And we need to work in that direction. Now, with that, I think we will come to the close of this session. Very interesting. Ashish has got some question.
So you have this question, I think maybe some of you also will have. So I started working in microfluidics not long back, just maybe little over a decade. So one question I often encounter is that, this field has been here for a while, and did it really, deliver for what it's supposed to be? And although I see, many systems that have been developed, many commercial, things have also come out to market. But beyond that, many times, although, because I happen to work in this field, I just do what I like to do. And although many times, my efforts are really oriented towards, making it work and towards some application. But I think, is that something that we should be doing, that continue working in microfluidics? Okay, you do something that you like to do, but then if it happens to be going towards some application, be happy about it. What is your take on that?
Good question. Is it worth doing microfluidics? Basically, the question is it worth doing microfluidics?
if I just like to do, can I continue to do, or do I have to do keeping only? I should only do if it meets certain application. So maybe that's the question.
Yeah.
So yeah, you want to go talk first?
Yeah. I mean, so maybe I mean the previous question got a lot of emotions risen, so I didn't want to comment on that. But I mean, I find it useful to think in this way that there are certain things that are on the horizon, which are visible to lots of people, and they're all crowding together to somehow reach that. That's something that is on the horizon, and everybody can see that it's going to make a difference. It may or may not, because it depends on a lot of other things, whether it turns out to be useful in the end or not. Depends a lot on the translational ecosystem, the financing ecosystem, and all of those other things. But there are also other things that are over the horizon which are sort of visible to only very few people. And they are trying to pursue that, and maybe that will come on the horizon in future. But that won't happen unless somebody is pursuing it. So I think at the basic level, there are people who are trying to look over the horizon and see what is there. And those are at the basic research level. And then there is once it comes on the horizon, there's a crowd of people that is chasing it. They may reach there, or it may turn out to be a mirage, we don't know. But so I think there needs to be some fraction of people who are looking over the horizon as well. And those are sort of lonely people who are convinced about their own ability to see things that nobody else can. But I think that is very necessary, even though that may not be visible to a large number of other people around there. So I think, yeah, I mean, as a group, we need some kind of self-awareness of, what we are going after. And going after over the horizon things are things that are visible to only a very small number of people with a lot of creativity and imagination. And once it comes on the horizon, then it also depends upon your motivations and stuff like that, your ability to collect people to follow a common goal and things like that. And both kinds are required. Yeah.
So my question to you is, do you like to be paid for what you do? If money is no issue and it satisfies you, keep doing it. And so I think, but if you want to get paid for what you do, you have to start reaching some sort of compromise. And with this opportunity, I'd like to mention this. We talked, this is the fundamental question from before. I mean, there are structured ways, of course, also to categorize research a little bit. But of course, the research this categorization has a purpose, all right? So for research with no purpose, let's say, probably what I'm going to say does not apply, and that is the technology readiness levels, all right? So people fund all kinds of research from technology readiness 1 to 9, I think is the last one. So effectively, then you find where you are in a scale, and NASA, I think, came up with that first, and then in there, you can basically find where you are and then see how far you are from your goal and so on and so forth. So there are previous steps. This is not the first time this question has been discussed. And then you can see where you are in that scale and see if it's worth doing it or not. All right, so
I would like to bring a different thing into this domain of discussion. So I really don't think the question is that sensible. I agree completely. If you want to do it, do it. And I don't completely agree that you have to have a common goal. I think if we all had a common goal, then it would be too structured and we wouldn't see right and left, and the unseen and unplanned things would not be discovered. But there are cases where you have to ask, should I be doing this? But I don't see that right now in microfluidics. And the obvious cases are ethical questions. Should I build a hydrogen bomb? I mean, you could ask the question, should I be doing that? Or political. Do I want to work with India? Do I want to work with Russia? Do I want to work with the United States? Those are questions that I don't see arising. So I don't think we're yet into that environment where we have to pose that question with microfluidics. But it might come. Who knows? I mean, especially the ethical questions might come eventually.
Yeah, so I'd just like to give a comment back, Ashish, that I do think that the field has delivered, so I don't agree with you that it hasn't delivered. I mean, we are all the people here, and for a reason that over the years we have actually developed a lot of and sort of put down a lot of knowledge?
Actually, the question was whether the field has delivered enough.
Well, the field.
I think it's clear that
that's the crystal ball question again, right? I mean, we have still questions to answer, so we will keep going.
I would, yeah, please.
I mean, I would look at it. I would look at it slightly differently. And to me, microfluidics is just a tool. It's just one of many tools. And instead, I would ask, what can you do? If you need microfluidics, do it. Use it. But I don't think there's any more really fundamental questions, or there are fundamental questions about microfluidics that you'll come to when you can't do something that you really want to do in that tool. Then you'll develop some new tool. But I think there's so many things that we can and should do, both fundamental and have a big impact on society. And I think already there are many things that use microfluidics, some of which were not even things that you ever thought were microfluidics, but they are essentially microfluidics that have changed the way science works, that have changed the way society works, that I just see the same thing happening. I see just more and more happening. And microfluidics is a valuable tool that we use. But maybe instead of focusing your research just on microfluidics, you can ask, what are the things that I can do? What are the important things that I can do? What questions can I ask? And use microfluidics as a tool if you need it.
So this question I can close with an answer with 3 examples. See, a particular field, as you asked, that whether it has delivered, whether it will develop in a particular way, there is no rule. You take the first example of electronics. People started asking questions even 30 years back, where is the end of it? We don't see even the end of it, even today, right? 22 nanometer technology, then 18 nanometer technology, and we don't know. It's still going. So some fields are like that. Some fields are like, superconductivity. In 1980s, when we were starting to do research, everybody was jumping at superconductivity. In fact, there was Indian cryogenics conference where all people working in cryogenic system fitted to a small room, and the big auditorium in the conference was devoted to only superconductivity. Because everybody jumped into it, and everybody said it's round the corner, room temperature superconductors. It didn't happen in that particular field. So 90% of those people exited from the field. But those 10% who were interested really in superconductivity continued, and superconductivity is still a field. But may not be encompassing thousands of researchers, a small community, but they have done quite well in their own way. Now, this is the second one, that something goes up and then something goes continuously up, something goes up and comes down. Then there is the greatest example of something comes cyclic. And there is a story, you ask any AI specialist, that AI has been having a cycle of 10 years. Every 10 years people said, now AI will become important. And it failed. But now we see there is really a shoot up into that. Probably previous cases, we didn't have enough computing power or things like that to handle big data and all that. And today it has arrived. So it may be cyclic, but at one point it may shoot up. And shoot up means how many years it will go, nobody knows. It may be that within 10 years, all the AI algorithms are within your mobile phone, and then nobody talks about AI. This is very normal. Let's jump to something else. So there is no rule which way a particular field will develop. Microfluidics, I still think there is enough potential in that. Particularly I see in bio. Of course, I don't think things like previously there was quite a number of papers where they said we'll build a fluidic computer. There was a build computer logic circuits on fluidics. That has not been successful. But in other cases, both at the chemical reactor level and the biological level, it has delivered something and it has shown promises which are not completely out of the place. So I still feel very much positive about the field, and I don't think that there is any reason to be worried about the future.
Thank you.
So with this, you would like to conclude the session. I will ask if, I won't ask everybody, if anyone has got a last message to give, they can give. So, because there is no last message to give, I presume that the field is pretty open. And let's go and do. Thank you very much.
Thank you, Professor Das, for moderating the session, and thanks all the members here.